Back in 2017, a small group of researchers quietly published a document that was just 8 pages long. And the crazy thing is, they absolutely were not trying to invent some sci-fi machine that could pass the bar exam or, diagnose complex diseases or write flawless software code. Not at all. They literally just wanted to build a slightly better language translator. But instead, they accidentally drafted the blueprints for a completely new kind of artificial mind.
So, that brings us to the core question of this explainer. How exactly did a single, highly technical 8-page paper unlock the modern artificial mind? I mean, how do we get from a clunky machine that is actively struggling to translate a basic sentence to the astonishing large language models that we interact with today? Well, to put it simply, it all comes down to a fundamental, ground-up shift in how computers process information.
Welcome to the overview effect, where you zoom out and everything changes. I am so glad you're here with me today, because right now we are going to track the actual evolutionary leap that changed artificial intelligence forever. Let's dive in.
Okay, Section 1, the illusion of memory. To truly appreciate the magnitude of what happened in 2017, we kind of have to look back at the dark ages of artificial memory. For decades, teaching a computer to simply translate human language was just an incredibly frustrating endeavor. And that's because you can't just swap words one by one. It doesn't work. Different languages possess completely different grammatical skeletons. A verb that sits at the start of a sentence in English might actually belong at the very end in German. So to translate accurately, the machine desperately needed a way to remember the past. But early neural networks, they operated on iterative, left-to-right processing. Think of it like a really slow, linear assembly line. The machine would read words one by one, continuously passing along a rolling mathematical summary of what it had read so far. In computer science, they called this rolling summary the hidden state. Basically, the output of the previous round served as the input to the next.
But there was a massive, glaring flaw with this hidden state approach. We can compare it to a tiny, heavily erased index card being passed down a long line of people. So the crucial point here is this. Perfect early memory inevitably turned into degraded final context. By the time this theoretical index card reached, say, the 50th word at the end of a long paragraph, the summary was completely degraded. It was a mess. The machine suffered from a literal kind of amnesia. If a paragraph began with a specific, absolutely crucial noun, the machine would simply forget it by the time it needed to generate the concluding verb. It was basically trying to memorize an entire book with using a single, tiny sticky note, and it just wasn't working.
But, this immense frustration is exactly what pushed the field forward. Starting from traditional pattern recognition, we actually hit a huge milestone in 2014. A researcher named Dmitry Bogdanov proposed a brilliant escape route. He realized, hey, the machine shouldn't just rely on that tiny index card. What if it could dynamically turn around and look backward at previous words? This was the birth of the attention mechanism, and it was a huge step for sure. But there was a catch. The computer was still trapped in that slow, linear factory. It still had to read the sequence one step at a time. It was a band-aid, not a cure.
Which brings us to Section 2, the 2017 architecture pivot.
So a team at Google Brain looked at this 2014 attention mechanism and made a truly bizarre, radical proposition. Throw the entire sequential process away. Literally, just scrap it. They completely abandoned the linear assembly line that AI had relied on for years. Instead of passing a note down a line to be read in order, they introduced the transformer. And this new way of thinking is wild. It places every single word into a massive open room to be viewed simultaneously. It allowed the machine to see everything at once, entirely removing the bottleneck of reading left to right. It's like turning on the lights in a dark room.
Let's get into Section 3, decoding the attention mechanism.
So how does this open room actually work in practice? Let's take the highly technical math of the neural network and translate it into accessible visual geometry. This trick, this absolute game changer, is called self-attention. Formally, it's a mechanism allowing a machine to dynamically weigh which earlier words matter most when guessing the next one. To calculate these incredibly complex relationships, the transformer assigns every single word 3 distinct geometric avatars. I want you to imagine a word literally splitting into 3 floating shapes: a hollow mold, a jagged key, and a solid cube.
Let's walk through this 3-part dance because it's brilliant. First, we have the query. The query acts like a radar, or a hollow mold, actively seeking a perfect match. Second, the key. The key acts as a beacon of light, constantly broadcasting its specific shape. Now, in that massive open room, the machine physically tests the query for one word against the key of every single other word in the sentence, all simultaneously. And if the query of an adjective perfectly matches the key of a noun, boom, the mathematical signal is absolutely massive. Once the machine knows the exact percentage of focus, how much these two words care about each other, it brings in the third avatar, the value. The value provides the final substance. So the machine might take exactly 80% of the value of the word car and mathematically fuse it with the word fast to synthesize a brand new, highly contextualized understanding. It's building meaning out of geometry.
Moving on to Section 4, Pre-training the Foundation Model.
All right, now that we understand the micro-level geometry of how a single word works, how do we actually build a functioning artificial mind from scratch? I mean, how do we scale this up? It all starts with the pre-training phase. This is where we take our newly built architecture, that massive open room, and feed it insane amounts of raw, unlabeled text. We're talking about trillions of words, literally scraping internet texts, books, Wikipedia, research articles, the whole shebang. And at this stage, the model isn't answering questions. It's not chatting with you. It's simply learning to predict the next word over and over and over again. By doing this billions of times, it is passively developing a broad, deep, foundational understanding of human language. It's learning the very shape of how we communicate.
Section 5, Fine-tuning the AI Assistant.
But here's the thing. A foundation model that just predicts the next word, that isn't very helpful for a user who wants to ask a specific question. If you ask it a question, it might just predict another question. We have to move from a broad, general model to a specialized tool that humans can actually interact with. So once we have our massively pre-trained foundation model, we have to fine-tune it on smaller, highly specific labeled datasets. It's a fork in the road. One path might lead to a classifier, which simply sorts data into boxes. But the other path, the one that powers the modern chatbots we all use, involves fine-tuning the model on instruction data sets. This crucial step is what transforms our broad pattern guesser into a highly useful conversational personal assistant that is capable of following complex human directives.
Let's just pause and compare where we started to where we are now. To put it into perspective, traditional machine learning methods were really only great at categorization tasks. Think about your email, looking for words like prize or free to categorize an incoming message as spam. That's traditional AI. But modern large language models display what we call emergent behaviors. Because of the transformer's ability to see everything at once in that open room and perfectly weigh context using that geometric math, these models can do things we never explicitly program them to do. They can follow incredibly complex instructions, conduct nuanced contextual analysis, and generate coherent, highly original text. It is an immense, staggering leap in capability that completely changes how you and I interact with technology every single day.
Section 6, the Universal Pattern Engine.
Okay, here is where we really need to zoom out for a final perspective shift, because engineers quickly realize that this trick, this self-attention mechanism, isn't just restricted to human language. It is a universal pattern engine. Because the transformer fundamentally just calculates relationships, you can feed it almost anything. Think about it. You can feed it a sequence of musical notes, and the query of a specific chord will seek out the key of a complementary harmony. You can feed it the amino acids of biological DNA, and it will calculate exactly how a protein folds in three-dimensional space by measuring the gravitational pull of the molecules. You can even feed it the raw pixels of an image, and it will calculate exactly how the shadow relates to the light. It's mind-blowing.
That little 8-page paper from 2017 did not just solve the problem of grammar, it solved the fundamental problem of context in a chaotic universe. It gave the machine a way to look at a fragmented, messy world and mathematically calculate exactly what matters. It was never just about words. It was about teaching a computer how to pay attention.
When you look past the illusion of a reading mind, you realize something profound. Comprehension is just the beautiful optimization of geometric space. If a machine can learn to pay attention to the fundamental geometry of our universe, what will it notice next? Thank you so much for joining me for this explainer, and we will see you in the next one.